Now let us talk about Frenkel excitons. These are observed in systems like sodium chloride, sodium bromide, and potassium chloride, potassium bromide, etc., etc. So what you see is that these are tightly bound, in the sense the excitation lives on a single site more or less. So, and this is more common actually in the organic solid state. And in organic solid state, this is also important for many electronic applications that people are using organic molecules for. For example, things like organic solar cells and so forth. How do you model these? To model them is quite simple. You think of the following, that is, you have various molecules at various sites, and at site I, let us say that I excite it. So when I excite it, it becomes, the excitation is like this, and this excitation actually can travel along the lattice. How? What is the mechanism by which it can travel? I will come to that one. The molecules experience dipolar interactions. In fact, it is well known that these dipolar interactions are the ones that are responsible for van der Waals forces, and even if the molecule has no dipole moment, it will still have dipolar interactions because of momentary dipoles or fluctuating dipoles that exist in the system, as one describes. So because of that, the dipolar interaction Hamiltonian, the perturbation term is just given by sigma over k mu k dot mu k plus 1 by r cubed minus 3 times mu k dot r mu k plus 1 dot r divided by r cubed, where r is the unit vector along the intermolecular axis, and mu are the dipole operators. We are actually doing a quantum chemical calculation or quantum mechanical calculation. So mu's are operators, and I am not looking at dipole moments per se. It is not a classical calculation. So given this, what happens is that we can think of H I and T is very similar to H crystal in the tight binding model. So in the tight binding model, what did we have? We had H crystal was actually equal to minus H cross squared by 2m del squared plus V periodic, and we had the transfer integral T was then given by, between I and I plus 1 was given by I H crystal phi I plus 1. So in our case, H0 the unperturbed Hamiltonian which replaces the kinetic energy term in the crystal Hamiltonian is the molecular Hamiltonian, is a molecular Hamiltonian of an isolated molecule. So, and if psi I is the ground state of the ith molecule, and psi I star is the excited state of the ith molecule, then the transfer term for the exciton has a the following. Then the transfer term is given by T I comma I plus 1, let me call it tilde. So, tilde just means that it is for the exciton. Okay. So, this is given by psi I star psi I plus 1 H interaction, which is a dipolar interaction, times psi of I plus 1 star. So, supposing I put the details of the H interaction and then I define the transition dipole moments mu I to I plus 1 as psi I mu I mu I to I star. So, this is the transition dipole moment for the molecule I to go from ground state to the excited state and at the position I. Okay, so, if I do that, then what happens is that the psi star I plus 1, rather I had put the star on the other one, H interaction psi I plus 1 star will turn out to be nothing but mu I to I star dot. So, these are all vectors mu tilde I plus 1 to I plus 1 star divided by r cubed minus 3 times mu I to I star dot the unit vector times mu tilde I plus 1 to I plus 1 star dot r unit vector divided by r cubed. Now, so this is the transfer term, and the exciton actually hops from side to side by using this. That is in the sense that I can say that the Hamiltonian matrix will have the form and let me call this as equal to some term like omega, not omega, maybe it is better to use some other symbol. Let us use this, let us say that this is equal to some delta, okay, delta I plus 1. Okay. So, the Hamiltonian matrix in that case will be given by the following, that is, it will be a tridiagonal matrix. On the diagonal is the excitation energy, let me call it E naught etc., because okay, and then on the off diagonal I will have delta and delta. So, it will be a tridiagonal matrix much like the tight binding matrix. The tight binding matrix was having the following, right. So, you would be having in the tight binding matrix the energy, let me call it the TB matrix. So, the energy would be epsilon 0, etc., and then I would be having T, etc., T. So, this was the matrix and very similar to that one. So, then what happens is the following, that is, we will have a dispersion of the excitonic band which is 2 delta cos K A, where A is the intermolecular spacing and K is the wave vector. So, it will take exactly the same value as before. So, K will take the value 0 plus minus 2 pi by L A plus minus 4 pi by L A, etc., etc. Now, what is interesting is the sign of delta. What will be the sign of delta? This depends upon the orientation of the transition dipole moments. Mu I to I star. So, how these transition dipole moments are oriented at different sides? Well, let us assume two different orientations. One of the orientations is, let me take it as let me take this to be x, y and z, so that I have a right handed coordinate system. Let us assume that all the transition dipoles are oriented in this direction. Okay. So, these are the lattice sides. Then delta will be minus 2 mu z I mu z I plus 1 by r cubed, because r and mu are in the same direction. Which I call the z direction. So, this is one limit, and the other one I can have is the following. So, I can have the transition dipole moments aligned this way. So, in this case delta will be mu z I plus 1. So, this is I to I star, I plus 1 to I plus 1 star divided by r cubed. So, In case A, which is what I write here, and this is case B. In case A, the delta is negative, and in B, delta is positive. This is very important because I will come to that one, why it is important. So, in case A, where delta is negative, the dispersion will go like this. You have the ground state molecule, all the molecules are in the ground state. So, k is equal to 0 is the state, and let me make it vertical. Sorry, that is the k axis. No, this is energy, I am right. This is k, and what we have is, because it is negative, it will show a dispersion like this one. This is minus pi by a, and this is plus pi by a. And this is the excited state, so this is the exciton dispersion. In the other case, the exciton dispersion will look like this. Now, what is the difference? The difference is in the optical properties. So, supposing we are looking at an optical properties, optical emission from the excited state. What happens is that here we are going to excite it. So, I can excite it, say, let us say from here to there, and in this case I will excite from here to there, and also let me also mark the E naught, which is the isolated molecule excitation energy. So, the emission will also take place at the same point. So, even if you excite anywhere you excite it, okay, you can excite it here, it will come down to this place and then it will emit light. I will tell you why it comes down to that. And here on the other hand, the excitation is somewhere here, the excitation migrates to the band edge and then tries to emit to the ground state. So, here the emission is also from the minimum of the band to the ground state. The reason why this happens is because in organic molecules, in photochemistry of organic molecules, there is a rule called Kasha rule. What Kasha rule states is the following, that is, we can excite a molecule to any state in the same multiplicity, in the same spin multiplicity, that is, okay. Otherwise, it will be spin forbidden. That is, I can take, for example, so let me take the ground state to be somewhere here. So, let me assume that the ground state is a singlet and the surface is S0, and then I have excited states which can be some excited state there, another one there. So, let us say one more excited state, let us say. So, these are called S1, S2, S3. So, let us assume that you excite from S0 to S3. The emission, it says, is that the emission always takes place from S1. emission is always from S1 to S0. Okay. That is to say that I may excite from S0 to S3, but because of various internal conversions, which means that system goes from S3 to S2 to S1. So, the internal conversion from Sn to S1 is very fast, a few femtoseconds maybe, because the molecule just has to vibrate a few times and then it is gone into the next potential energy surface, and that crossing takes place, internal conversion takes place because of the terms which violate the Born-Oppenheimer approximation. Okay. So, and then emission is from S1. The emission is intense if S1 to S0 is allowed transition. If it is an allowed transition, then emission is intense. Otherwise, weak emission. So, when you are looking at singlets, you call them, that is, if the emission is from the excited state of same multiplicity as the ground state, then it is a fluorescence. So, you say the system has got very weak fluorescence if the S1 to S0 is not an allowed transition. So, now let us come back here. If we apply the Kasha rule and also the rule that crystal momentum should be conserved, you see that in this case, in case B, the crystal momentum is not conserved, whereas in case A the crystal momentum is conserved. Because of Kasha rule, what happens is, from the ground state you excite it to this state, and this is a high energy state, then it just comes down to the lowest energy and then tries to emit radiation. Whereas here, even if you excite somewhere here, because of the Kasha rule it comes down to k equal to 0 and then emits. So, you see in the case of A we have very strong fluorescence and in B weak fluorescence. So, here it is strong fluorescence and this one is weak fluorescence. So, the aggregation of type A, aggregation of molecules in type A is called J aggregate. And the aggregation of type B is called H aggregate. And what you know from this one is that in the J aggregate we have redshift in absorption, from the isolated molecule case, and emission is intense. In H aggregate, there is a blue shift in absorption and very weak emission. These kinds of aggregates are actually seen in organic solids, and these excitons are localized excitons. So, here we discussed Frenkel excitons, are localized and show different emission behavior, emission or fluorescent behavior. Depending upon the aggregation. Now, let me come to another case which is also interesting in molecular physics, molecular crystals, crystal physics of molecules. That is, supposing we have two identical molecules within a unit cell. So, this should actually remind you of in case of atoms, this is like two hydrogen atoms per unit cell or a dimerized lattice. Very similar to that is what we are talking about, a dimerized lattice. So, here is a dimerized lattice, but it has got two molecules per unit cell instead of two atoms per unit cells. So, now what happens to the exciton spectrum? Now, since you have two molecules, okay, identical molecules, let us say that these two molecules are psi A and psi B at two different sites in the unit cell are the states of the molecules at sites A and B in the unit cell. And then what happens? These are degenerative. Okay. For example, psi A star psi B is degenerate with psi A psi B star, because both of them are identical molecules, and so there will be a degeneracy. Now, when we have dipolar interactions, this degeneracy is lifted because what you have is, if you set up degenerate first order perturbation matrix, then what you have is the following, that is, you will have the energy E naught corresponding to the excitation, and then I am assuming the off diagonal matrix elements are real, and I will have delta is equal to psi A star psi B H dipolar psi A psi B star, and E naught is the energy of psi A star or psi B star. Then in this case what we have is we get two states. This leads to two split excitonic states in a unit cell. So one of them will have an energy E naught, the energies will be E naught plus minus delta, and the states are phi plus minus, okay. And phi plus will have the wave function psi A star psi B plus psi A psi B star, and minus will have plus minus. So this is very much like the hydrogen molecule chain. So you had the 1s orbitals of hydrogen atoms in the molecule, replaced by sigma 1s and sigma star 1s, and delta was the energy difference between the sigma 1s and the sigma star 1s. So it is very similar to that one. What I will do is I have now got the energy levels of the states within the unit cell, and then I will try to obtain the band structure corresponding to these, but I will do that in the next lecture because it will take a little bit of time. So we will meet again in the next lecture and discuss excitonic band structure when you have two molecules per unit cell. Thank you.